The emergence of AI-driven 3D model generation tools like Trellis2 marks a significant leap in digital asset creation. Developed by researchers at Microsoft, Trellis2 leverage machine learning to generate textured 3D models from 2D images, offering a revolutionary approach to 3D asset creation. While this technology holds immense potential for game developers, filmmakers, and hobbyists, its current limitations, particularly in mesh topology, optimization, and structural integrity, prevent it from being directly usable in high-end production environments. This short review explores how Trellis2 works and its capabilities, why AI-generated meshes are unsuitable for games, focusing on topology flaws like undefined edge loops, poor UV unwrapping, and non-optimized geometry. The benefits of AI-generated 3D models for professionals and hobbyists in gaming and filmmaking. Trellis2 is an end-to-end AI system that takes single or multiple images as input and outputs a textured 3D mesh. The process involves neural radiance fields-inspired techniques to infer 3D structure from 2D inputs, differentiable rendering to refine geometry and textures, automated UV unwrapping and texture mapping for a complete asset. The result is a highly detailed 3D model that can be used for visualization, prototyping, or further editing in tools like Blender, Maya, or Unreal Engine. Despite its impressive visual fidelity, Trellis2's output suffers from fundamental topological and structural issues that make it unusable in game engines without extensive manual cleanup. Let's explore the key problems. Game engines, Unreal Engine, Unity, and 3D animation pipelines rely on clean, well-structured meshes for deformation, rigging, and skinning. AI-generated models often lack consistent edge loops, making them deform poorly when animated. Subdivision and smoothing. Many AI models have irregular polygon distribution, leading to artifacts when subdivided. Hard surface modeling. Mechanical parts, like the robot in the scene, require sharp edges, proper chamfers, and clean creases, which AI often misinterprets. Game engines require low poly bases with proper topology for efficient rendering. Fewer polygons equal better performance. Modularity. Game assets must be easily edited and reused. Collision physics. Poor mesh structure leads to unnatural physics interactions. Excessive polygon count, which is overkill for real-time rendering. Non-manifold geometry, isolated vertices, overlapping faces, and holes. Lack of modularity. AI-generated models are single-piece meshes, not broken into logical components for game engines. While Trellis2 generates textures, the UV unwrapping is often suboptimal. The UV layout is packed on one single texture for the entire generated mesh. No consideration for texture atlas optimization, which is important for game engines. Overlapping UVs cause seam artifacts. Distorted UV islands lead to texture stretching. AI-generated materials may not be PBR, physically based rendering, compliant, leading to unrealistic lighting. Missing material IDs. Game engines require separate materials for different parts of a model. Games require reusable, interchangeable assets. AI-generated models are single-use, not easily broken into parts for different game variants. Non-parametric, cannot be adjusted for different sizes or configurations. Lacking metadata, game engines need proper naming conventions, LODs, level of detail, and collision shapes. Despite these limitations, AI-generated 3D models offer tremendous advantages for both industry professionals and hobbyists. AI can quickly generate playable assets for early game design stages. Artists can sketch a concept in 2D, and AI converts it into a 3D model for testing. Reduces the need for expensive 3D sculpting for low-detail assets. Amateur developers can create basic game props without advanced modeling skills. AI can generate plausible textures from images, saving hours of manual texturing work, useful for fantasy or stylized games where realism is less critical. AI can infinite procedural variations of objects, for example, different weapon designs, terrain features, helps in procedural world generation. Film studios can quickly generate 3D placeholders for VFX shots before full production, helps in virtual production, for example, Unreal Engine filmmaking. Indie filmmakers can create detailed 3D assets without hiring expensive 3D artists. Concept artists can test character designs in 3D before final sculpting. Real estate and product designers can generate 3D previews from photos. Students learning 3D modeling can use AI as a starting point before refining topology. Hobbyists can create personal projects, for example, sci-fi models, fantasy creatures, without deep technical skills. While Trellis2 and similar tools aren't production-ready for games yet, future advancements could include AI-assisted retopology, automatically fixing edge loops and optimizing meshes, procedural rigging and UV unwrapping, AI that automates rigging-ready topology, game engine plugins, direct export to Unreal or Unity with proper LODs and collision, hybrid workflows. AI generates a base mesh, but artists refine critical parts. Trellis2 and similar AI tools are revolutionary for rapid 3D generation, but they cannot replace traditional 3D pipelines due to topology, optimization, and workflow issues. However, they augment the creative process by speeding up prototyping for both games and filmmaking. For game developers, AI-generated assets will likely be used in early stages, concept art, or as starting points rather than final in-game models. For filmmakers, they provide a cost-effective way to visualize ideas before committing to full 3D production. As AI improves, we may see hybrid workflows, where humans and machines collaborate. AI generates the base mesh, and artists refine, retopologize, and optimize for production. Until then, Trellis2 remains a fascinating glimpse into the future of 3D creation, but one that still requires manual polish for real-world use.